Hello everyone, my name is Hossein Rahbar. I'm a PhD student at Cardinal University in Canada. I would like to present our work on a simple model for gas phase synthesis of nickel nanoparticle, which widely used in battery technologies and catalysts. Nickel nanoparticles are made by gas phase synthesis using nickel tetracarbonyl as a precursor. Upon heating, nickel tetracarbonyl decomposes into nickel and carbon monoxide, and nickel atoms form incipient nanoparticle clusters. These clusters grow by surface growth or coagulation and form fractal-like agglomerates. Agglomerate morphology evolves also by sintering at high temperature. Depending on the temperature time history of the reactor and the strength of coagulation compared to sintering, soft or hard agglomerate or even spheres may form. The characteristic sintering time of nickel agglomerates was obtained from net growth rate of nickel dimer considering different mass transfer mechanisms. We found that surface diffusion and green boundary diffusion are dominant processes. To validate the calculated characteristic sintering times, we use them with a monodisperse population balance modeling to predict sintering of size-selected agglomerates in a flow reactor, where agglomerates with an initial mobility diameter of 60 nanometer are heated at different temperature for 7 seconds. The change in the mobility and primary particle diameter are monitored. At temperature below 450 Kelvin, sintering is weak and agglomerate mobility diameter and primary particle diameter do not change much. For temperatures above that, mobility diameter rapidly decreases while primary particle increases as agglomerates merge into each other due to sintering, which compared by TM images. For temperature above 800 Kelvin, sintering results in a compact agglomerate, where mobility and primary particle diameter reach a same value of 32 nanometers. After model validation, we use them in a simple monodisperse model to predict nickel nanoparticles evolution in a flow reactor. Nickel tetracarbonyl rapidly decomposes at the beginning of the reactor, which results in a sharp increase in the number density of agglomerates. Also, agglomerates rapidly collide due to high concentration, and their fractal dimension rapidly decreases from 3 to 1.8, which is for fully ramified agglomerates. And additionally, volume equivalent diameter constantly increases due to collision, which results in a larger agglomerate with more primary particles. However, primary particle diameter grows monotonically due to the low sintering rate. In conclusion, we use a new characteristic sintering time in population balance modeling to predict the evolution of nickel agglomerates from the very earliest stages of sintering. Thank you.